Nice. So as usual, I'm going to share my screen, and today we are going to take the bottom-up approach where so bottom-up, like I show you some theory and then we do some coding to support the theory that we had. Okay, so I'm going to use the software that we've been using all this while, and then I will give you some explanations. And our focus today is going to be on what is known as the perceptron. And this, therefore, becomes our introduction to deep learning because that is the foundation, okay? Perceptron. Okay. Now, I'm going to give you a very rough definition of what a perceptron is. A perceptron basically is an artificial implementation of a single neuron in the brain. I want you to take this statement at face value because people usually make a mistake and say, yeah, neural network is modeled after the human brain. The truth is, humans do not yet understand how our brains work. We have been fortunate to be able to see at a minute level things that are happening, how brain activity can be measured in electric current and changes in voltage and all that, but we don't really understand how the brain works completely. So the neural networks are modeled loosely after the human brain. Like the inspiration has been borrowed from how we think the human brain works. So who knows what we discover in the next 10 years, which will prove that we were wrong or we were right. So until then, you take it as neural networks are inspired by the way the human brain works, okay? Now, if you go to your kitchen right now, you open your skull, you take a piece of your brain and you put it under a microscope. You see minute cells known as neurons, okay? I'm not going to draw it properly because I'm struggling with even writing on this bamboo thing, but it looks something like this with a nucleus and then something like this. These guys here at the tail end, we call them dendrites. So this is biology. Okay, and the whole of the activity is happening at the center here. How the neurons work is that they receive signals from the other body parts. As I'm talking to you, you are receiving signals from me. You don't see it, but your brain is actually receiving signals from me. That is why we can measure brain activity to know what you are thinking. Like people who cannot type with their hands can now write books because you can put electrodes around their brain and then they think sentences and a computer system will be writing the sentences that they are thinking of, all because everything that is going on results in brain activities. Me moving my hand, if I have one of the devices here, if I put it on my head, you will see different brain signals based on what I'm doing. If I move my left eye, different brain signal. If I move right, if I clench my teeth, if I open my mouth, different brain signals are happening. Now, biologically, the things that are enabling these things to be possible is this neuron, and it's a cell. So information gets into the neuron and it comes to this central part of it, which you can loosely call the nucleus. And it does some computation. After the computation, we say the neutron either fires or not. When it fires, it means it does its own computation and it passes on the, like whatever computation it did onto the next neuron. So there could be another neuron here and the dendrites are going like this. And then that one has its nucleus somewhere here. Okay, so this guy will do some calculations and then pass it on to this guy. Now, The dendrites do not touch. At least that is what biology is telling us. They don't touch, but they are very close. So where this thing is happening is called the synapse. We are taking a bit of, we are borrowing inspiration. So some information gets in there, and you have these in your brain, these cells, millions of them. That is what is making it possible for you to see. That is what is making it possible for you to taste. That is what is making it possible for you to learn, for you to hear. What happened?
I think my network.
Okay. All right. So you can see my screen, or I should still, you can see it now, right?
Yeah.
Okay. So millions of these guys in the brain, and we are borrowing it to be able to implement it in code today. How do perceptrons work? I've already told you that the perceptron is a software implementation of a single neuron, because in neural networks, we put together several perceptrons. That is what gives us a neural network, okay? So in software, we implement a perceptron as something like this. And you will put in information into your perceptron. These information are going to be features. Yesterday, I explained what features are. Features are columns in your data set. Not always columns. If you have tabular data, it's the columns. But if you have unstructured data like images, you know, when I give you 1 pixel of an image, it doesn't make sense to you. So we call those things unstructured data. If I give you some audio file and you pick one segment of it, it doesn't make sense. Those ones are unstructured. But any data that is laid out as a table, we call it tabular data. And those ones, the columns are the features. If it's unstructured, then any point in the data is part of the features, okay? So you put in your data into the perceptron. The perceptron does some computation here, and it produces an output. So usually we use perceptrons for classifications. So yesterday we did simple regression where you are putting in numbers to get a number out. In classification, you are putting in some data point to get a category out. Like your data is such that there are groupings in them, and you want to train a model to be able to discover the patterns that result in classifying a particular data in a particular group, so that when you show it data that it has never seen before, then it will use those patterns it has learned to make the classification for you. Okay, so before you use a perceptron, the first thing you need to make sure of is that your data is linearly separable. When I say linearly separable, it means if you plot your data, let me do it here. If you should plot your data, usually you need to use 2 classes for a simple perceptron like this. It is good for handling just 2 categories, okay? So let's say I have some data, and I have feature 1 here, I'm plotting feature 1 here, and I'm plotting feature 2 here. Now, it can be such that there are different groupings of the data. So I'm using I don't know what color this is. It looks like pink to me. I have issues with color, so if I'm wrong, forgive me. Then I'm going to change this to something that looks yellow. So if you plot your data like this, and you visually inspect it, and you see that it is possible for you to draw a line to separate the 2 categories, then this data set is linearly separable. It is not the same as if you had a data that looks like this. Let's say we have this, and we have this. Such data statistically is noise. You can't see any definite pattern in this one. And probably the best separation you can do is to maybe go something like this, like this, like this, like this, this. I see, I'm trying, but I will still get either of the other colors in the other side. So this is not linearly separable. The moment you start curving to separate them, you should know that it is not linearly separable. So the first thing that will tell you whether you can apply a perceptron to your problem is if the data set is linearly separable. And you do that after you do what is known as exploratory data analysis. So exploratory is you making some plot to do visual inspection, calculating mean, average, variance, and stuff like that for you to get some statistical information. Now, let's not just deceive you that, okay, if perceptrons can be used for just linearly separable data, how come neural networks can work with nonlinear data? Neural networks can work with that because it is made up of multiple perceptrons, and your data is high dimensional. So each perceptron is going to be responsible for a particular dimension. So it can still divide those hyperplane into two in multiple directions. That is what makes neural networks powerful. So we have this basic thing called a perceptron, but you chain them together and they become very powerful. Now, how does the perceptron achieve its work? We are looking at data like this. I said tabular data, okay? So I have a first column we call X1, X2, X3, and the Y is our classification, okay? And then we have rows of data like this. So in our notation, the entire data set, excluding the output, so the Y is our output or the class, what we are going to learn to predict. So everything here forms part of our giant X matrix. That is our data set. And this becomes the labels. The Y becomes the labels that we want to learn how to predict. So in today's example, we are going to use a data set about flowers. And for this data set, people have measured the sepal length, the petal length, various attributes of the flowers. And there are three grouping of those flowers, but we will separate two of them and we train a perceptron to be able to learn how to classify whether, based on the sepal length and the petal length, this flower is type A or type B. This is not only applicable to that data set. If I can change the data set and give it just audio recordings of me saying, let's say 9 and 4. Okay, so two classes. One audio is saying 4, another audio is saying 9. I can throw it to this, and when I say 9, the perceptron can tell me what I said. When I say 4, it can tell me as simple as it looks over here. So now we're going to learn the mathematics behind the perceptron. So I'm going to draw it again. Our features will come in like this. So we have X1, X2, X3, and it is going to predict some output Y. I'm going to use a classical example to help you understand this. The first thing that the perceptron does is it looks at the number of features in your data and it creates a vector of weights. Okay, so it is going to multiply XY, S1 by W1, multiply X2 by W2, multiply X3 by W3, and add a bias term to it. Yesterday, we saw why we need a bias term. it is still needed, even though yesterday our problem was purely a simple line, but even in high dimensions, we still need a bias term, and I explained that yesterday. So before training, this weight vector is going to be initialized to random values, or it could be zeros, or it could be ones. Which approach you choose comes with its own advantages and disadvantages, which are quite advanced stuff that we will not talk about, but we will do random initialization. Okay, so you saw in our data sets that for each row, we have a corresponding Y, okay? Now, the perceptron is going to start on the assumption that to get Y, it has to do this. So it has to do this, your input data. So it has to do the summation. So I is equal to 1 to, let's say, n, and then it has to do x I plus w, times. So I'm using this to represent times wi plus b. The b is your bias term. So what it means, this formula here is basically saying this: y is equal to x1 w1 plus x2 w2 plus x3 w3 plus b. Okay, it's the same formula written in different ways. So the n is like, if you had multiple features all the way to n, then you have xn over here. That means we add this and then we have wn. Okay, now the perceptron knows that it is starting with random weight. So it is not even expecting that the predictions it will come up with is going to be what is in your data set. So it will say it is trying to generate y hat. We use y hat to represent the prediction from the perceptron, okay? Because like yesterday, it needs to calculate a loss. I think you people are too silent. Tell me, are you understanding, or there is something you want me to take again?
Actually, I'm raising my hand, but I think you didn't see my hand actually.
Okay, sorry. Maybe talk when instead of like using the emoji. Sometimes I'm not seeing it.
All right, that's fine. Okay. So many thanks for your interpretation. It's really exciting, bro. So I'm asking about each model we are talking about. It has each its own hyperparameters.
Yes. So the size of the hyperparameters is going to depend on the number of features in your data. If the features are 100, then you have 100 hyperparameters. This is for just the perceptron, but if it is a neural network, it will depend on even the number of layers in there.
Yeah. Okay. So my question here: how can we optimize these hyperparameters and find the best value for this model?
So we will talk about that too. That is the gradient descent. So yesterday I explained a bit of it, but today we will implement it in code.
Right.
So we will use gradient descent because Eric was asking if we can use brute force to find the correct weight and bias, and I said no, brute force is the wrong way, because you see, when I write the formula, you see that when you change W, it will affect the loss. When you change B, it will affect the loss. So the question is, how do you change each one of them? But calculus helps us to answer that with what is called partial derivatives. So we will use that.
Right.
Okay. So any other question? Okay, so I'm going to, let me go to the grid view so that I can see all of you, your faces, to know who is lost and who isn't. Okay, all right. So we have this formula now. Because the perceptrons start off with random weight, it is expected that it will make mistakes in the predictions. Okay. So then we have to evaluate our loss. And our loss is that my boss in the video there. Olatunde, that's you, right?
Yes, please.
Okay, Charlie, it's been ages.
Yeah.
So we need to find a way to estimate the loss. How wrong is the perceptron in its prediction? Let me give you this example here so that we use it all along. So we have this x1, x2, x3, and then we have our y, okay? So let's say some value can be here, can be here, can be here, and you can put you in class 0. Some value, we can put you in class 0. Some value 1. Some other values put you in class 0. So we are interested in getting our perceptron to predict the y's correctly. That is why we call it fitting. We call it fitting because we start with wrong weight and bias. Then through mathematics, we make sure that we find those numbers that will let us uncover the patterns in the data. Okay. So we need to come up with a loss. So yesterday you saw that one of the, and it's actually a very common loss function. And it is the loss is equal to the summation from I equals 1 to m. And I told you that m is the number of rows in your data set. So we have y, the predicted y minus this y, okay, all squared. And to make the calculus easier, we multiply it by 1 over 2m. It is mean because we are finding the summation of all our errors, because you see, y hat is the prediction. Y is the actual class. So we subtract the prediction from the actual class and we square it so that whether it's negative or positive, we are interested in the magnitude. Then we sum it all. Then we divide by m to get the mean. But because of these two here, if we do it 1 over 2m, then when we have to do derivatives, you know that if I have to calculate derivative of this, it's going to be 2 times 1 over 2m, this y hat minus y. The square go away because you need to subtract 1. This is simple calculus. So then if I do this, then I do this, then I'm getting what? The summation of y hat minus y divided by m. So the 1 over 2m is something my teacher, Andrew Ang, taught me that made the calculus simpler for me.
So what do you mean by, so what do you mean by the derivative here? So that's the interesting thing.
Yeah, so the derivative, I'm calculating the rate of change of L with respect to my the W and the B. I'm calculating how does the loss change when I change weight? How does the loss change when I change B? Because you see, our prediction involves these terms. W, B, and in calculus, when you take a derivative of something, you are actually calculating rate of change. And we are interested in knowing how should we change W and B to get the loss to be as small as possible. You understand, Mohammed?
Yes, it is. It is interesting.
Okay. So we have this loss function. Then comes partial derivative. I'm repeating the formula again. So we have y hat here is equal to the summation of I equals 1 to n. We have xi wi, and then we do our plus b over here. And then we said our loss is equal to 1 over 2m sigma I is equal to 1 to m. And then please, you don't need to be able to do this maths to do deep learning, but because of the understanding I want you to have, that's why I'm teaching you this. Very soon we write the code. So then we have y hat minus y all squared, okay? And yesterday I showed you that because of this squared here, I want to limit the mathematics, so it's not everything I'll prove, but because of the squared term in it, if we should plot our loss against, let's say, just one of the weights, so I'll put WI here, we get something that looks like this. In the same way, if we plot L, so let me say W1, W2, we get something like this. It is the same if we plot how loss is changing with respect to B. It is going to be something like this. Then this becomes a multi-dimensional problem. I have drawn them individually, so it's 2D. But in multi-dimension, it will be like even more than 3D, but we can only visualize to 3D. We can't go beyond 3D. So if I should try to do this in 3D, it's going to look something like this. And then we'll get a graph that looks like a bowl. Okay, so let's say this will be W1, this will be W2, and this will be my L. So our interest is we want to find the lowest point, because you see the lowest point corresponds to the smallest loss we can get. And the point where we get the smallest loss is the projection onto the W1 axis and the projection onto the W2 axis. So it means that this point, W1 here, W2 here, gives us the smallest loss, which is what we are interested in. Now, the thing is, our weight is a vector. W1, W2, W3 is a list of numbers. So we can't do this one by one, because if I change W1 alone, you see, if you look up here, our formula involves all the W's. So if I change any one of the W's, my prediction will also change. So it's not like, yeah, Eric.
Yeah, a quick one, right? So looking at this graph, the 3D one, you see, if you can plot such a graph with this data, why don't you rather, instead of doing gradient descent and then moving from the top side to the find the minimum, why don't you rather try to...
I already know your question, and I won't let you finish. You can't plot beyond 3 dimensions. And most of the data you'll be working with has more than 3 columns. So I get what Eric is doing, and it's a smart way to think. What he's asking is, instead of doing this whole neural network stuff just to find the lowest point of a graph, why can't we simply plot the graph and eyeball it? We can look at it on a graph and see that this is the lowest point. But the thing is, we can't plot beyond 3D. And if you want to do image recognition, even a 2x2 pixel image has gone beyond that. A colored image has gone beyond that. If you want to do audio recognition, we have to, even 1 second of audio can give you about 10,000 data points. Eric, do you get it?
Yeah.
And it is impossible for you to plot. There is no hyperplane plotting that you can do that can let you, in fact, you will be confused. If you try to plot 4D, you'll be confused right now. So imagine 5D, 10,000D, 1 million D. You get a point.
Yeah.
That is why there's the need for an iterative approach to the solution. Okay.
Yeah.
But that's actually a good question. And it is thinking like this that creates novel ideas, like challenging the status quo. It's not like because, oh, people said this is how we do it. This is how we always do it. Okay. All right. So now we need to come to partial derivative, and then we start writing code. So I'm going to clean the graph a bit. Yes, 10 minutes. When the 10 minutes is up, we will break, and then we come back so that everybody can refresh their mind after this math. Okay, I hope I can find a way to erase this thing at the faster pace. So this is the biggest erase I'll get. All right, no problem. I just need some small space to do partial derivatives with us. Okay. All right, so we have our loss function. Now we need to know how our loss is going to change with respect to each of the parameters. The weight and the bias, we call them parameters, okay? So then we are interested in calculating the L, the DW1. We are interested in calculating the L, DW2, the L, DWN, so up to the nth weight, and then the L, DB, because we also want to see how changing the bias is going to affect the loss.
Hello, Pi.
And yeah.
I don't want the mathematicians to arrest you. So use del instead of the capital, the delta.
Okay, so I can just choose to do this.
Even this is still total. So this particular D is the best. The one you just cleaned is the best.
I'm struggling to write with this bamboo here, so don't worry me with your pettiness.
Okay.
So now that we have this, then we need to use partial derivatives. You see, you use partial derivatives when you are calculating the derivative of something with respect to multiple other things. Because it has W1, W2, W3, and then B, you can't simply do it. So if you are a calculus person and then you go into details, this whole thing becomes simple. So your the L with respect to the entire weight, so I'm using just W here, is going to be equal to Y hat minus Y multiplied by the entire X, the X that goes into it. We don't need to prove this because already it's becoming too much. And then we also have our DL over B. How this is going to change is basically going to be simply Y hat minus Y. I'm making your life simple for you. But for those of you who are calculus expert and all those things, if you take time to look at it, this is what you are going to get. So now, if we know our DL, DW, DL, DB, then this will help us to update W and B. Okay. Now let's see why this formula is going to work. Then we take a break. L is equal to sigma I is equal to 1 to M Y hat minus Y all squared 1 over 2M. And now we know that the L, Eric, you've confused me in these things that I don't know whether I should write delta or this. So this is now going to be our Y hat minus Y times the entire row, and then this dB is just going to be Y hat minus Y. Now, pay attention. If you haven't paid attention, this is the point where you understand why the algorithm works, okay? Let's say in our data set, so I'm drawing a rough data set here, X1, X2, and Y, dot, 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 let's say 0, 1. Now, let's see what happens with Y hat. I'm going to show you the update rule. So we say that our W is equal to W, okay, W minus alpha times DL dW. I told you yesterday that alpha is the learning rate. It controls how fast learning is happening. And if you set it too high, the behavior is different. If you set it too low, the behavior is also different. So that one, we call it hyperparameter. So the parameters are the one that is not in your control. That one, the model itself has to modify them. A hyperparameter is something that you, the AI practitioner, need to use your own intelligence and intuition to set. So hyperparameters, alpha is a hyperparameter because you will set it. That one, the model cannot learn it on its own. There are ways to automate it, but for now, the model will not learn it on its own. Now, see, let's say the actual y was 0 and the model predicted 1. Let's see what is happening here. So if y was 0 and the model predicted 1, we get what? 1 minus 0. Okay? But if the actual value, was, let's say, if it predicted 0 when there was supposed to be 1, then we get this. So over here, it will communicate to the model that your y hat is greater than what we expected. If it's greater, we want to take a descent. We want to go down. We want to go down. We want to go down. So alpha times this expression here is going to reduce w, because w minus alpha times the derivative. However, if it predicted something smaller than what we were expecting, this becomes what? -1. So what we get here? We get w minus, then we have alpha times -1, which becomes what? W plus the rest of the term. So then it tells you that you are too low, climb up. I'm giving you some mathematical intuitions here. And if you struggle to understand this, I'm giving you some video on my channel where I did the same explanation, but maybe in the comfort of your own room, you will be able to understand it better. So I'm going to send that video to you right now, so that maybe after today's session, for those of you who are interested in the mathematical aspect, you can still go through it. But like I said, because of the libraries that exist, if you just want to build models, you don't have to worry your head over this math. But knowing the mathematics is definitely a plus to you. Where is Perceptron? I have a video on Perceptron. I think it's on chapter 5. Yep. Okay. So I'm sending the video link to you via chat. Please bookmark it before the session ends. And take a quick break, and I'll see you in the next, where we start writing code for all these boring mathematics that we have done. Okay? So
Yeah,
see you in a few
quick
minutes.
one. Hello.
Okay. Yeah.
Yeah, in differentiation, in calculus, you see, anytime you take the derivative of something and you equate it to 0, right? That means you are actually computing the minimum.
The minimum.
Yeah.
But again, it is highly dimensional. It's not just with one variable. If it was just one variable, then you just calculate the gradient and equal to 0. Then you solve for x.
Okay.
But this is many w's.
Okay.
Eric is still trying to find a way to debunk AI. Okay, see you in I'll see you in 2 minutes.